Welcome to Power Electronics Advanced Grid Control. In this training, we will progress from foundational components to complex grid systems across four core modules. First, power semiconductor devices, covering the transition from traditional switches to next generation silicon carbide and gallium nitride. Second, rectifier topologies, focusing on multipulse configurations and harmonic reduction. Third, modulation techniques, exploring advanced space vector PWM. Finally, devices, examining how controllers like OPFC enable dynamic grid stability. The evolution of high power electronics began with thyristor based devices, which dominated the 20th century. The silicon controlled rectifier, or SCR, was the first major breakthrough. It offers massive current capability but has a latching nature. Once turned on, it stays on until the current drops to zero. To solve this control limitation, the gate turn off thyristor, or GTO, was developed. It allows engineers to force the device off by applying a negative gate pulse. While both devices can handle extreme power levels, their primary drawback is low switching speed, limiting their application in high frequency modern systems. Welcome to the era of modern industrial power electronics. Today, the insulated gate bipolar transistor, or IGBT, and the integrated gate commutated thyristor, IGCT, dominate the medium to high power landscape. The IGBT revolutionized the industry by combining the simple voltage driven gate of a MOSFET with the high current characteristics of a bipolar transistor. This unique internal structure makes the IGBT incredibly easy to control while maintaining low switching losses, establishing it as the standard for motor drives. Meanwhile, the IGCT represents the ultimate evolution of the traditional GTO. By integrating the gate drive directly into the device, it achieves exceptionally low conduction losses and high efficiency at massive power levels. As we reach the limits of traditional silicon, power electronics are transitioning to wideband gap materials, specifically silicon carbide and gallium nitride. The term wideband gap refers to the significantly higher energy required for electrons to jump from the valence band to the conduction band. This physical trait enables a much higher critical electric field, delivering exceptionally high breakdown voltages and drastically lower on-state resistance. Furthermore, their superior thermal conductivity allows for high efficiency operation at extreme temperatures, greatly reducing cooling requirements. Though categorized together, they target distinct domains. SiC MOSFETs are the industry standard for high voltage, high power grid and converter applications. In contrast, GaN HEMTs excel in high frequency environments, elevating switching speeds from standard kilohertz up to the megahertz range. Moving from individual components to system topologies, let's examine the foundational 6-pulse rectifier, widely used in industrial power conversion. This configuration utilizes a three-phase bridge circuit. When fed with a standard three-phase AC supply, the semiconductor devices commutate sequentially. The resulting output is a DC voltage characterized by 6 distinct ripples per fundamental AC cycle. While functional, this ripple introduces significant harmonic distortion. Specifically, the 6-pulse topology generates dominant 5th and 7th order harmonics on the AC side. These low order harmonics are highly problematic. They increase the total harmonic distortion, or THD, causing localized heating and reducing overall power grid efficiency. To overcome the severe harmonic distortion inherent in the standard 6-pulse rectifier, large scale industrial applications employ the 12-pulse rectifier configuration. This advanced topology utilizes a specialized wide delta wide transformer to feed two separate 6-pulse bridges. The fundamental engineering principle here is the precise 30-degree electrical phase shift introduced between the star and delta secondary windings. When we combine the outputs of these two phase-shifted bridges, destructive interference occurs for specific harmonic frequencies. This causes the most problematic lower order harmonics, specifically the fifth and seventh, to completely cancel out, drastically reducing total harmonic distortion. As a result, the first significant remaining harmonics are the 11th and 13th orders, simplifying filter design. To understand how we control power flow in a three-phase system, we must examine the mathematical foundation of the controlled rectifier. The fundamental equation for the average DC output voltage is derived by integrating the peak segments of the three-phase AC sine waves. This gives us the formula V underscore DC equals 3 root 3 over pi multiplied by the line voltage V underscore LL and the cosine of alpha. Here, V underscore LL represents the RMS line-to-line voltage. This sets the absolute maximum DC voltage our rectifier can produce. The critical control variable is alpha, the firing angle of the thyristors. By delaying the firing pulse, we increase alpha. As alpha increases toward 90 degrees, the cosine term drops, reducing V underscore DC. This is the essence of dynamic power control. Now we transition to inverters. The fundamental technique for converting DC back to AC is sinusoidal pulse width modulation, or SPWM. SPWM generates switching signals by comparing two waveforms, a high-frequency triangular carrier wave and a low-frequency sinusoidal reference wave. When the sine wave's amplitude exceeds the triangular carrier, the switch turns on. As the sine wave peaks, the resulting pulses become wider. Whilst FTWM effectively minimizes lower order harmonics, it has a major limitation. It only utilizes about 86% of the available DC bus voltage. As we move to high voltage applications, traditional two-level inverters face a major challenge. The high DC link voltage places immense stress on individual semiconductor switches. Rapid switching also creates severe dV over dt stress, which can damage equipment insulation. The solution is the multi-level inverter. Instead of switching directly between full positive and negative voltages, multi-level topologies connect multiple devices in series to create intermediate voltage steps. By stepping the voltage through 3, 5, or more levels, we construct a staircase waveform that closely approximates a pure sine wave. This dramatically reduces harmonic distortion before filtering. Consequently, we achieve a significantly reduced filter size and higher overall efficiency for grid applications. As modern power grids grow increasingly complex, maintaining dynamic stability is critical. This brings us to AFS, flexible AC transmission systems. Historically, grid control relied on slow, wear-prone mechanical switches. FAST revolutionizes this by applying high-speed power electronics for instantaneous response. This advanced family of controllers includes the SVC, STATCOM, SSSC, TCSC, and the unified UPFC. By dynamically regulating voltage, line impedance, and phase angle, these devices maximize power transfer capacity and prevent system collapse. Let's examine shunt controllers, comparing the static VAR compensator, or SVC, with the static synchronous compensator, STATCOM. Both provide fast reactive power support to maintain voltage stability, but their operating principles differ significantly. The SVC is an impedance-based device. It uses thyristors to switch capacitors and reactors, altering the network's equivalent impedance. In contrast, the STATCOM is a voltage source converter, or VSC based device. It actively synthesizes a voltage waveform to inject or absorb reactive power. This architectural difference becomes crucial during grid faults. Let's look at their VI characteristics. The reactive current provided by an SVC drops linearly as grid voltage falls. However, a STATCOM can maintain full capacitive output current even when the system voltage drops significantly, offering superior performance and stability. Moving from shunt to series compensation, our primary objective shifts to directly controlling the transmission line's effective impedance to maximize active power transfer. The thyristor controlled series capacitor, or TCSC, achieves this by placing a thyristor controlled reactor in parallel with a series capacitor. This topology creates a dynamically variable reactance, effectively shortening the electrical length of the line. Conversely, the static synchronous series compensator, or SSSC, represents the VSC based evolution of series controllers. Instead of altering physical impedance, the SSSC injects a controllable AC voltage directly in series with the line, independent of the line current. Looking at the power angle curve, we see the profound impact. Decreasing effective reactance or injecting series voltage significantly raises the power transfer capability. We now arrive at the most versatile and comprehensive FUS device in modern power grids, the Unified Power Flow Controller, or UPFC. Unlike individual compensators like the SVC or TCSC, the UPFC combines both shunt and series architectures into a single, cohesive, and highly advanced control system. It consists of two massive voltage source converters. The first is connected in shunt with the transmission line, while the second is connected in series. Crucially, these two converters are coupled back to back, sharing a common DC link capacitor. This unique topology allows active power to flow bidirectionally between them. The true power of the UPFC lies in its unprecedented flexibility. It can simultaneously and independently control all three fundamental parameters of AC power transmission. It regulates bus voltage, adjusts line impedance, and shifts the phase angle all at once. By dynamically directing both real and reactive power flow, the UPFC unblocks congested transmission corridors, serving as the ultimate tool for dynamic grid stability. As we transition to modern power grids, the integration of volatile, renewable energy sources introduces a critical challenge: the reduction of traditional mechanical inertia. In conventional grids, massive spinning generators provide natural kinetic energy to buffer disturbances. However, solar and wind are inverter based, lacking this physical inertia. When a sudden disturbance occurs, such as a sudden drop in wind power, it can trigger severe power oscillations and voltage dips, threatening dynamic stability. This is where dynamic grid control devices like FUS and advanced power electronics become essential. They inject reactive power and synthesize virtual inertia in milliseconds. By rapidly damping these oscillations, power electronics ensure that modern, renewable heavy grids maintain robust dynamic stability under all operational conditions. We've traversed the landscape of modern power electronics, building from the ground up. At the foundation, wide bandgap devices like SI and GaN provide unprecedented efficiency. Moving up the hierarchy, we explored converter topologies. Utilizing 12 pulse rectifiers and fundamental voltage formulas allows us to significantly reduce harmonic distortion. These converters are driven by advanced modulation. Techniques like space vector PWM maximize DC bus utilization for multi-level inverters. Finally, at the system level, these blocks culminate in FACS devices, providing the dynamic control essential for the modern smart grid.